Alright, we're going to continue on and wrap up 1.2 today. So we need to talk about two things. One, periodic function and reference angle. And those are nothing alike. Periodic functions are functions that repeat every so often. For example, weekdays, those are periodic by 7, which means every 7 days, that days repeat. If today is Thursday, 7 days from now it's going to be Thursday, 14 days from now, any multiple of 7, they'll repeat. The clock works in 12 hours or 24 hours if you want to go by military time, So we have a lot of these repetitions, things that happen periodically. They repeat always. So associated with a periodic function is what's known as the coterminal angle, which means you land at the same place. Coterminal angles are two angles that share the same initial side and the same terminal side. They are off by 2 pi or 360 degrees radians, 360 degrees, or 2 pi radians. Now you do notice that in a circle things start repeating after 360 degrees, which means things start repeating. So if I was to tell you, I go to this place on a specific day, if you count 7 days from that day, that means I should be at that place again. Or if I tell you, this thing occurs every 7 days, whatever today is, it's going to occur on the same day until that period stops. For circles, we are aware that an angle, and if I take this angle and I subtract 360, meaning I'm going to get this negative value. Theta and beta are coterminal. Why is that? They share the same starting point and the same ending point. They both start, so ignore that part right there. And if I have an angle, I could do this many different ways. Not that hard to see. I could say, well, look, there's an angle theta. If I am to take that angle and subtract 360, I'll get this. Now, if you want to see more angles, I could show you. We are going to do a lot of examples. And what if I took this angle theta and I subtracted that twice? Well, that's the same thing. Alpha, beta, and theta are coterminal. So coterminal angles, we're going to use that in this section and the next section. And reference angle is something we're going to adore. What a reference angle is, let theta denote an angle that lies in any quadrant, and in case you missed it, quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So, the acute is an angle between 0 degrees and 90 degrees, formed by the terminal side of the angle, and the x-axis is called a reference angle. So, 4 cases. Case 1, I'm in quadrant 1. Case 2, I'm in quadrant 2. Case 3, I'm in quadrant 3. And case 4, I'm in quadrant 4. So, theta, let theta denote, let's say this is theta right there. So wherever you stop, you draw a terminal side for theta. This is the initial side. For all of them, the initial side is the positive x-axis because those are in standard. So what you do, you go to that side right there and you run to the x-axis. This angle that you form between the terminal side and the x-axis, we say the reference angle. So any angle in quadrant 1 is its own reference angle. What if I went to quadrant 2? Well, the reference angle for theta now This is theta. The reference angle, the terminal side is right there. You're going to run from the terminal side down to the x-axis, forming a right triangle. The angle between the terminal side and the x-axis is the reference angle for theta. If I look at quadrant 3, in quadrant 3, the terminal side, that's where the angle terminates, and this is theta. The reference angle is always an angle between 0 and 90, so it's always positive. I'm going to take this side, and I'm going to run to the x-axis, always to the x-axis, creating a triangle, and this angle right here will be the reference angle to theta. And if I am in quadrant 4, assume this is where theta is. Let's say it's 310 degrees. That's theta. The reference to the angle would be actually running from the terminal side to the x-axis. So between coterminal and reference, I'm going to be able to figure out a lot of things that I need. Now, consider a unit circle. Consider a unit circle. That's what trig is based on. What's a unit circle? It's a circle in which the radius equals exactly 1. So assume I have a unit circle. If that's a 1 and that's a 1. If I want to figure out the walking distance around this angle, S equal R times theta. But this is a unit circle. What does the radius equal? And this is going to satisfy a lot of confusion, or hopefully clarify a lot of confusion. What's the catch? Theta must be in radians, in case you've forgotten. So theta must be in radians for this to work. Now, I'm still assuming we have a unit circle. If you pick a point x and y, well, if I run a line straight to it, wouldn't you say that's a radius, that's a 1? If I run down, wouldn't you say this is the x, this is the y? Now notice what happened if I try and figure out, well, theta, the reference theta, with this terminal point x and y is right there. If I take the cosine of theta, wouldn't that be the adjacent over the hypotenuse? And similarly, if I find the sine of theta, wouldn't you say that's the opposite over the hypotenuse? So what does that mean? That means in a unit circle, if I'm given a unit circle, the traditional x and y, I could replace by the cosine of theta and the sine of theta, as long as we're talking about reference angles, as long as it's running down to the x-axis. Well, that means what? That means I could really take x out and say that's the cosine of theta, and take that out and say that's the sine of theta. So on the triangle, I could say this side is the cosine of that angle, and this side is the sine of that angle. And now if I look at a right triangle, wouldn't you say that 1 squared equal cosine squared of theta plus sine squared of theta? So that's how trig defined those identities. And in trig, we say, well, hey, isn't the secant of theta 1 over x? And isn't x the cosine of theta? Isn't cosecant of theta 1 over y? Again, cosecant of theta is the hypotenuse over the opposite. Wouldn't that be 1 over sine of theta? And that's how we define the reciprocal identities. And tan of theta, again, I'm referring to this triangle right here. Tan of theta is the opposite over the adjacent. The opposite over the adjacent. And I could derive all the previous identities that I derived. And of course, similarly here, I could divide everything by sine squared. 1 over sine is cosecant. Cosine over sine is the cotangent. And sine over sine is 1. And I can go back to this and divide everything by cosine squared. 1 over cosine squared is the secant squared. Cosine squared over cosine squared is 1. And sine squared over cosine squared is tangent squared. And I could derive the previous identities as we did in the previous sections. And that's really how it works. So you really want to get into the habit of figuring that. Anywhere I see an x, if it's a unit circle, that's really cosine of theta. Anywhere I see a y, if it's a unit circle, that's the sine. Now, to get things going and really shrink your work drastically, you need to get a couple of things out of the way. You need to get all the reference angle for 30, 60, 90 and 45, 45, 90. And by using the reference angle, using trigonometry, and the triangle using geometry, I could figure out whatever's needed for this class. And let me show you how it works. And you should do this a couple of times. One time, what you do, you cut the quadrants exactly in half. And you say, well, let's see how this works. This is 0, this is 360 degrees. Half of that is 180. Half of that is 90 degrees. And if I cut this in half, half of 90 is 45 degrees. 45 plus 45 is 90, plus 45 is 135 degrees, plus 45 is 180, plus 45 is 225 degrees, plus 45 is 270 degrees, plus 45, 315 degrees, and 360 degrees. And you're going to come down and cut this into 3 equal parts. And you're going to say, well, look, we know this is 0, this is 360 degrees. Half of that is 180. Half of that is 90 degrees. Do you see that I broke this into 3 equal parts? 1/3 of that is 30 degrees. Once you know this, 30 plus 30 is 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. And you're going to come back and do this one more time, except now you're going to do it in radians. You're going to say, this is 0 and this is 2 pi. Half of 2 pi is pi. Half of pi is, you don't divide by 2, you multiply by a half. If you take 1/2 times pi, that's pi over 2. And this is half of that. 1/2 of pi over 2. If you multiply, that's 1 pi over 4. And now we go for fractions. 1 pi over 4, 2 pi over 4 reduced, 3 pi over 4, 4 pi over 4 reduced, 5 pi over 4, 6 pi over 4 reduced, 7 pi over 4, and 8 pi over 4 reduced. And we come here, say, look, this is 0, this is 2 pi. This is half of 2 pi, which is pi. Half of pi is pi over 2. Here we break it into 3 equal parts. You know what I mean? So we take 1/3 of pi over 2. That is pi over 6, that's this. 1 pi over 6. 2 pi over 6 if you reduce it. 3 pi over 6 reduced. 4 pi over 6 reduced by 2. 5 pi over 6. 6 pi over 6. 7 pi over 6. 8 pi over 6 reduced. 9 pi over 6. 10 pi over 6 reduced, 11 pi over 6, and 12 pi over 6. If you get those two down, it takes about 5 minutes to get those going. That's 1/3 of this class. If I'm talking about a unit circle, wouldn't you say this is 1 and this is 0? And x is -1 here and 0? The y is 1 and the x is 0, and this point is 0, -1. Trig says, look, get me the 45 degree, okay, it's not registering. cut this in half. This is the 45 degrees, or it is the pi over 4. And they say, look, if I was looking at a triangle in which this is 45 degrees and this is 1 radical 2. If I want the radius to be 1, I could do that by dividing this by radical 2, dividing this by radical 2, and dividing this by radical 2. So if you make that a 1, if this is a 1, then automatically, if you're talking about this being 45 degrees, this right here is 1 over radical 2, and this is 1 over radical 2. If you rationalize, and if I come down and say, all right, let's label the 30 and the 60. Those are the triangles I need the most. That's 30 degrees, and that's 60 degrees. Oops. So if you say 30 degrees or pi over 6, if you say 60 degrees or pi over 3, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. Well, if I drew the 30, 60, 90 triangle, if I say this is 30, isn't this 1, this is 2, this is radical 3? If I wanted to force this to be a 1, don't you divide this by 2, this by 2, and this by 2? And that means if you force this to be a 1, the x-axis will be radical 3 over 2, and the y value will be 1/2. And if you look at 60, those swap. That is the 1/2, and that's the radical 3 over 2. If I have those in front of me, if I get my test and I write those in front of me, I can answer pretty much anything that's needed. So let's start this section. I suppose I'll start that in the next video. In the next video, I'll do all of these examples. I have tons of them.